Welcome to a wonderful lecture this early evening. Two of the broadest puzzles in science today are the origin of life on Earth and the prospects of characterizing life elsewhere in the universe. The search for life, of course, has narrowed to locations that might have contained liquid water in the past, water being a prerequisite for life as we know it, and the closest such venue would be the planet Mars. A little over a year ago, as all of you know, the Mars exploration rovers, Spirit and Opportunity, bounced down on Mars to serve as robotic geologists. Their goals were indeed to gather evidence about past liquid water on Mars and the minerals that might have formed in that liquid water. Today, we are extraordinarily fortunate to have with us Dr. Steve Squyres, who's here to tell us about the latest scientific results from the two Mars rovers. He helped design and build and now operate all of the scientific instruments on those rovers. Dr. Squyres leads a team of 170 scientists and engineers that are conducting the day-to-day science operations, helping determine where the rovers are to drive, what pictures to take, and of course what sorts of rocks to examine and how to examine them. Dr. Squyres received his PhD at Cornell University in 1981, where he worked with world-renowned planetary scientists Joe Vaverka and Carl Sagan. He then went to NASA Ames Research Center here in the Bay Area for 5 years, doing more planetary work on a variety of topics in our solar system. And then he went back to Cornell, where he's currently a professor of astronomy. Dr. Squyres has worked on, as I say, a variety of topics, including not just Mars, but Venus, the moons of Jupiter, and even worked on asteroids. He's quite interested indeed in one of the moons of Jupiter, Europa, which he's helped ascertain may have liquid oceans underneath the surface. I should mention, too, that Dr. Squyres performs a number of infrastructural tasks that help science. He was, in fact, the chair of the NASA Space Science Advisory Committee for a number of years. He, of course, has received many awards. I'll just mention two of them. He was awarded the American Astronomical Society's Harold Urey Prize for Outstanding Achievement for a Young Scientist. And then a couple of years ago, he was named, actually a year and a half ago, was named by ABC World News Tonight the Person of the Week. And so, without further ado, let's all please welcome Dr. Steve Squyres.
All right. Well, thank you very much. Thanks, Jeff. People hear me okay? Is this on? It's on. Okay. I'm here tonight to talk about the Mars Exploration Rover mission, this mission of Spirit and Opportunity. I would like to begin by showing you a brief video clip. This is a computer animation. It was done by a student at Cornell, and it depicts the entire mission from launch through landing and operations on the surface of Mars, and we'll just give you a sense of how the thing works. This is Mars, the object of our affections. Actually, I think I'm going to want to bring the lights down a bit more because there's a lot of stuff to see on the screen, so whatever you can do to sort of bring the lights down so we can see the pictures a little bit more would be good. Mars is actually a really terrible place. It's cold. The average temperature is 60 degrees below zero. It's dry. If you took all the water vapor in the Martian atmosphere and you condensed it out on the surface, you would make a layer that's barely 1/100 of a millimeter thick. It's a desolate place. It is a place whose surface is not today suitable for life. And yet we have tantalizing clues that then in the past it was different. This is a picture from a spacecraft called Mars Global Surveyor. It shows a valley snaking across the Martian surface. That valley is less than 1 kilometer wide, and you can even look inside the valley. You can see the little channel through which the water flowed. This was carved by flowing liquid water on the Martian surface. You can't do this today. It's too cold, it's too dry. So this is telling us that in the past, conditions on Mars were different. They were warmer, they were wetter, they were somehow, in ways that we don't understand well, more Earth-like. Now, any geologist will tell you that where you have erosion, you will also have deposition. And the materials that had been eroded from these valleys have been carried downstream by the waters that carved them and have been deposited in low-lying regions to form layered sedimentary rocks. Now, a geologist will also tell you that one of the great things about layered sedimentary rocks is that they can contain and preserve a record of what conditions were like in the water when they were laid down. A geologist is like a detective at the scene of a crime. They're going out, they're looking at rocks, and what they're looking for is clues. Clues as to what happened here long ago. And if your geologist is equipped with the right tools and the right capabilities, they can go to a place where rocks were laid down and they can tell you something about what the conditions were like there in the past. And was it warm? Was it wet? And was it habitable? Was it the kind of place that would have been suitable for life? So we built 2 robot geologists and sent them to Mars. These are our 2 robot geologists. You can see Spirit here. Oh, that's good with the lights. Thank you. This is Spirit here in the foreground, all tricked out, just about ready to go to Mars. That's Opportunity in the background. She doesn't have her wheels on yet. I'm the good-looking guy in the white suit. This picture was taken only about 2 years ago in Florida. So it's been a very, very busy 2 years for us. This shows the science payload for the vehicle. The science payload on this vehicle comes in 2 parts. The first part is supported by this big white stovepipe of a mast. It consists of 2 instruments. One is a set of cameras, a pair of high-resolution color stereo cameras that we use to take most of the beautiful pictures that you have seen from the rover. Those are up at the top of the mast. And then there's also an infrared spectrometer. If you had infrared eyes, you'd be able to look off into the distance, and different types of rock would look different to you in ways that they don't in visible light. Limestone would look different from sandstone, would look different from granite, etc. They have different minerals, have their own diagnostic signatures. And so there's an infrared spectrometer here that lives inside the rover, looks up the mast, and uses those mirrors, uses a set of mirrors at the top as a periscope, basically, to look out and get more or less the same view of the countryside that the cameras do. And then, at the front of the rover, there's an arm. It's exactly the same dimensions as my arm. Shoulder, elbow, wrist. It's purely a coincidence that it's the same size. And on the hand, there are 4 fingers. There's a microscope for close-up imaging. There are 2 more spectrometers to tell us in detail what the rocks are made of. And then there's a device we call the RAT, R-A-T, the rock abrasion tool. If you see a geologist out in the field, they got the boots, they got the backpack, 6-pack of beer in the back. They got a rock hammer. They've always got a big old hammer. And the reason they have a hammer is the hammer is their tool for breaking open the rocks and seeing what's inside. Okay, when a rock sits out on the surface of a world for some period of time, it's exposed to the elements. Wind, moisture, sunlight, things that can cause changes in the composition of the rock, things that can change its character, things that can modify or even destroy the evidence. And what you want is you want fresh rock. You want fresh rock that hasn't been modified so you can tell what it was like when it was first laid down. Geologists use hammers. We use our rock abrasion tool. And you saw that in the video, and I'll show it again later. This is our spacecraft. This is the Spirit spacecraft hanging in the big thermal vacuum chamber at JPL where we tested it before sending it off to Florida. The spacecraft is built, and you saw this in the video, it's sort of like one of those Russian dolls. You know, where there's a doll inside a doll inside a doll, right? Okay, it's sort of like that. The rover folds up into a little compact package, goes inside the lander. The lander has these 3 petals that fold up around it, like the petals of a flower, and so you get this tetrahedral shape here. That is then encased in a heat shield, which protects the vehicle during its fiery descent through the Martian atmosphere, and a protective shell to go on the back. And then this big blue Frisbee-shaped thing It's called the cruise stage, and that has solar arrays and propulsion, the things that you need to keep the vehicle alive and healthy on its way to Mars. We dumped that off before we hit the top of the Martian atmosphere. We launched the summer of 2003, 2 beautiful launches from Cape Canaveral on Delta II launch vehicles. 7-month cruise to Mars. You get to Mars, you hit the top of the atmosphere going about 25 times the speed of sound, Mach 25, about 12,000 miles an hour. The heat shield takes out much of that energy, and then at about Mach 2, twice the speed of sound, we throw out a supersonic parachute. Those turn out to be very complicated to design and build. The vehicle is still rushing towards the surface. The lander descends on a long cord called a bridle. And so this is what the vehicle looks like as it's plummeting towards the surface, still going several hundred miles an hour. We had a terrible time with our parachute test. Our parachute test program produced failure after failure after failure. I remember there was a test that we did, beautiful day. We went to a gunnery range outside of Boise, Idaho, and dropped a parachute from a Chinook helicopter. It was at 4,000 feet, dropped the thing, you saw it fall away. And this was the chute design that we expected to take us to Mars. Chute blossoms out, makes a perfect orange and white bowl, and then it just ripped to ribbons, just exploded. We went through test after test after test. Finally, I love this picture. This is a picture of our very first successful parachute test. Took place right across the bay in a big wind tunnel at Ames Research Center. This took place 8 months before launch. When it worked, it was a beautiful thing to see, but it was scary. Then there are the airbags. What? That's an engineer at JPL being consumed by his work. The airbags inflate, rocket motors fire, you cut free, and you bounce, 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 and you bounce. The bouncing in the video was not exaggerated. In fact, the bouncing in the video, we kind of toned it down because, A, it looked a little too scary, and B, it goes on forever. But the bouncing and rolling takes quite a while. It's a spectacular thing to see. Once we land, then the thing has to open up. Of all the parts of this very scary mission, this was the part I was most scared about. Everything else at least had been done once before. Rocket launches have been done. Landing on Mars with airbags has been done. But this process of unfolding takes so many gears and springs and motors and hinges and latches that all have to work exactly right, or you're done. The mission's over. Every one of these critical deployments, what you're seeing right here, everything here that you're seeing happened automatically within the first hour after landing. And if any of these deployments, like the unfolding of the solar array or the camera mast coming up, didn't work, that's it. It's over. So at this point, this is the configuration the vehicle was in the first time it talked to us from the Martian surface. Solar arrays are out. There's power. You have a stable thermal situation. The vehicle is safe. It's not ready to go anywhere because it's still crouching down. It has to stand up yet. But at least at this point, it's not going to die. Here's the second part. This is even crazier. Watch this. There's a jack that lifts the thing up, and then watch what the front wheels do. Watch this. Those latches had better work. And now at this point, now we're a rover. Now we had naively thought that once we got to this point, once we got so that all the folding and unfolding and deployments and so forth were done, we would then be ready to just go monster trucking off the lander and onto the surface of Mars. And then we did some tests. And we concluded that no, it's a little more complicated than that. We had to build some ramps. And so you actually saw in the video, between the pedals as they unfold, there are these fabric ramps, very tough fabric. They're made of the very same fabric that the airbags are made of. And those fold out, snap into place, and those provide a safe exit path down onto the surface of Mars. There are other complications as well, like driving on irregular surfaces. The vehicle has a mobility system that is able to conform to the terrain underneath it. Just watch how this stuff moves. I mean, if we get a corrugated roof on Mars, we're ready for it. But watch, I mean, watch how this thing conforms and adapts to the topography beneath it. It is able to handle extreme excursions in the topography without the vehicle tipping over. Then there's the issue of how you actually drive it. Now, what I wish I could do, what I dearly wish I could do is I wish I could joystick it, right? I wish I could just, steer it in real time and go around rocks, and it'd be great fun, but you can't do it. And the reason is fundamentally Mars is too far away. The day that we landed, and it just got worse after that, but the day that we landed, the distance between Mars and Earth was so great that traveling at the speed of light, the radio signal from Earth to Mars took 10 minutes to get there. And then if something happens and it sends a radio signal back, that's another 10 minutes that way. So it's a 20-minute round trip to do anything. So if the rover's going towards a rock and I want to steer around that rock, 20 minutes later it's already hit the rock. So that doesn't work. What we've had to do instead is build into the vehicle vision, intelligence, and the appropriate level of cowardice or bravery to decide how to deal with obstacles. And we've actually, it's like a little, imagine a little slider, that's cowardly on one end and brave on the other. We can actually adjust the parameters and make it more courageous or less courageous depending on the terrain that we're in. But basically what it does, it's got this pair of googly-eyed cameras here on the front end of the vehicle and also on the back of the vehicle. There's two pairs of these things. They take these fisheye view pictures 120 degrees wide. The pictures that they take don't normally come down to the ground. Only the rover sees them. The rover takes a pair of pictures. It builds up in its own mind, in its own computer, a terrain model, a vision of the three-dimensional structure of the terrain in front of it. If it looks like smooth sailing, it will drive forward. If it sees something scary, it will go around it. And it's capable of making decisions and figuring out what to do when it gets to some rocks. Here's some actual data. This is Spirit driving. The first part of the drive, we've told it what to do, but now from here on, the vehicle's on its own. So it's making its own decisions now. So driving, things look good. Then there's a pile of scary rocks here. So what does it do? So it thinks a little bit, doesn't know what to do, and says, wait, I can do this. I can do it backwards. Makes that beep, beep, beep sound, Gets to another pile of rocks here, doesn't know what to do, figures it out, comes around here, gets to the end of drive, turns around, and it's done. They're pretty smart little guys. Then there's the rat. We talked about this earlier, the rock abrasion tool. This is the thing that we use to get inside of rocks. This was one of the most difficult pieces of the payload to develop. This thing is able to grind into solid basalt, one of the toughest rocks there is, using less electrical power than the light bulb in your refrigerator. Now, the rat is, in essence, a power tool. And as with all power tools, you have to devote a lot of thought and care to how you use them. You've got to worry about testing. And we did a lot of testing because we didn't want to have anything like that. I thought the wheel coming off was a nice touch. All right. I don't know why I put that in there. Sorry. It is a fiendishly complicated machine. Okay, I show this picture to people and they say, oh, God, what a mess. What did it look like when you finally got it done? No, that's what it looks like. On the surface of Mars today, that's what Spirit looks like. They are incredibly complex machines. But on landing night, they both worked. And these are the first two panoramas from Spirit and from Opportunity that we got down. Let me tell you about what we found. I'll start with Spirit. Spirit went to a place called Gusev crater. It's this impact crater right here. This is a topographic map of part of Mars, just a small part just south of the equator. The red stuff is high, the blue stuff is low. The crater is about 100 miles in diameter. There's nothing particularly noteworthy about it except this. There is a great big dried up river valley flowing into this crater. Okay, and that sets it apart. You don't find that very many places on Mars. Now this channel, this thing here, was carved by the flow of liquid water. Okay, so it's impossible for me to imagine how that could have happened without there once upon a time having been a lake in that crater. Big hole in the ground with a dried up riverbed flowing into it. Now there's no water there now, none in the valley, none in the crater. But sometime in the past, we believe that water flowed here, that water accumulated in that crater. There was a lake. And the stuff that was eroded from here must have been deposited in there. So we went there looking for sediments. We went there looking for sedimentary rocks that were laying down in this lake that we believe was there long ago. We landed, and this is what we saw. It's flat. That's good. It's good for driving. There's lots of rocks. That's good, because we went there to look for rocks. But the rocks are small. That's good, too, because they don't present a lot of obstacles for driving. So it was a very encouraging view from the standpoint of moving around, getting from here to there. We figure, okay, we'll at least be able to drive around in this stuff. But even in our first view, look for layered rocks there. You don't see them. Okay, so even our first view, we began to think, maybe this isn't quite what we expected. Now, we looked off in the distance, and at a distance of about 2.5 kilometers, roughly 1.5 miles away, there's this spectacular range of hills. We named them the Columbia Hills after the Columbia Space Shuttle. There are 7 summits in the range, and we named one for each of the Columbia astronauts. Our vehicle was designed to last for 90 days, 90 Martian days, and over its lifetime drive 600 meters, roughly 600 yards. Okay, that stuff was 2.5 kilometers away. It was out of reach. Nice scenery, but nothing we could do with it. So we decided to focus on the rocks at hand. The first rock that we looked at was this. It was one that we named Adirondack. It's this tall. We really worked this one over. We looked at it with our infrared spectrometer, with our cameras, with our microscope. We put a hole into it with our rock abrasion tool. We looked at it with our alpha particle X-ray spectrometer, our Mossbauer spectrometer. We hit it with everything we had, and it's a piece of lava. It's a piece of lava. It's a piece of basalt, one of the most common volcanic rock on Earth. Mars faked this out. Mars faked this out. There was a lake in this thing once upon a time. There must have been. There were sediments there. Must have been. But what we came to realize was that after the sediments were laid down, the sediments were probably laid down 3 billion years ago. A lot can happen in 3 billion years. Okay, and we believe now what happened was after the sediments were laid down in the lake, lava was deposited on top of the sediments, burying the good stuff under a bunch of volcanic lava. Volcanic lava is very interesting stuff, especially if it's from another planet, but it's not what we went there looking for. So this was a disappointment. Now, the good thing about having a rover is that if you don't like the neighborhood that you're in, you can go somewhere else. And so we did. This is one of my favorite pictures from very early in the mission. This is sort of Spirit looking out a rearview mirror. You can just barely see the lander at the top of the screen there. This shows what our plan of attack was. We landed where this green dot is. About 300 meters to the northeast was an impact crater, 250 meters in diameter, that we named Bonneville. So we thought, let's go there. The idea being, an impact, and we didn't bring a backhoe with us, we didn't bring a shovel, but we do have big holes in the ground in the form of impact craters. And the idea is this impact would have excavated through the boring stuff and cut down into the good stuff. So the idea is if we go up to the rim and look in the hole, maybe down in the hole will be the layered sediments that we were looking for. So we figured we'd go to Bonneville, do our thing there, explore as long as we needed to, and then if we still had any rover left, we'd head off in the general direction of the Columbia Hills because there's no place else to go. This is a very cool picture, and it's going to be tough to see, but look carefully. This is a picture that was taken from orbit on day 100 of our 90-day mission. There's the parachute. That bright dot there is the lander. That dark, tiny spot there is the rover. You can actually see the tracks that we made as we laboriously worked our way up to the rim of Bonneville Crater. We looked inside Bonneville and we saw a bunch of sand and more lava, but no layered rocks. It was a bitter disappointment. It was a 60-day struggle to get to the place from which we took this picture, and we looked in, and there was basically nothing of major interest there. So there we were. Now, at this point in time, we had a decision to make. We had a vehicle that had been designed to last for 90 days. We've now been on Mars for 100, so the warranty is expired. We are 2.5 kilometers from anything different, really, from what we're parked on. The Rover, warranty is expired. Nobody's going to make any guarantees that it's going to last any longer. So what do? Do we figure this thing's going to drop dead in the next week or 2 or 3 or the next month or so and just decide to look around at the rocks at our feet and try to make the best of the situation? Or do we trust the vehicle and try to go to the hills? We decided to do the latter, put the pedal down and sprinted, Rover speed, across the plains. Our maximum drive was 124 meters in one day. And we reached the base of the hills on day 156 of our 90-day mission. And in a space literally no more than that, as we crossed from the plains to the hills, everything changed. And we have not seen a piece of regular old basalt since then. It's all different. This shows Husband Hill, named after Rick Husband, the commander of Columbia. As we were approaching it, we're about 400 meters out now. Let me give you a little geography lesson here. This is Husband Hill as viewed from the north, so we're looking to the south. So we came in from this side. So we came in across the plains from here. The first part of the hill that we got to right here was something we called the West Spur. Okay, west is that direction. We spent a lot of time here. We spent about 6 months on the West Spur. Fantastic place. I'll show you some of the rocks there, but this is where we made some of our most interesting discoveries. Then we worked our way across the northwestern flank. This was tough going here. For some reason, this was very sandy, very slippery. We made very slow progress through here. This is a real quagmire. We finally got up to a place. This is the summit ridge of Husband Hill. The summit's there. This is the summit ridge, which we named Cumberland Ridge. This valley over here, which isn't labeled, we named Tennessee Valley. And we got the place where we reached the crest about 6 weeks ago was a place that we named Larry's Lookout, named after a person on our team who had advocated going there. And so that's basically the path that we followed. Now let me show you what we have found. When we climbed up onto the West Spur for the very first time, we found actual bedrock. Now, bedrock is really important to geologists. When you see loose blocks of rocks sitting around, you really don't know where they came from. Okay, they could have come from right there, or they could have come from someplace else and been transported by some geologic process. The beauty of finding bedrock is, this is the neighborhood it grew up in. It came from this place. So we found our first exposures of bedrock. This is an outcrop that we call Longhorn up on the West Spur. You can actually see the rim of Gusev crater about 40 miles away through the haze there. This is looking up towards the summit of Husband Hill from the West Spur. And as we began to explore the rocks on the West Spur, we started to see things completely different. For the first time, we found layering. We found actual layering in the rock. These are images that were taken with our microscope. That frame is only 3 centimeters, a little more than an inch across. And look at the layering. It's got very, very fine layering in these rocks. Never saw anything like that on the plains. We found exposures of bedrock that were made of very soft, crumbly rock. The stuff out on the plains was hard. It's very hard, tough basaltic lava, and it's a good thing we had a diamond-tip grinding tool because, boy, it was hard to fight through this stuff. Compared to that, this stuff was like cottage cheese. We just went right into it. Very easy, very soft. That's telling us something about the history of this rock. The chemistry was completely different. This is a sort of complicated plot, but what it shows, this is a list of all the different chemical elements that we measure. Silicon, titanium, aluminum, so forth. Okay, and what we've done here is we've made a plot in which we compare the composition of that rat hole that I just showed you to the rocks out on the plains. We're just dividing one by the other. We're comparing them. And this is a logarithmic scale, so this is a factor of 10 more, this is a factor of 10 less. If the rocks were identical, they would line up. We would see a perfect flat line corresponding with 1 going right across here. It's nothing like that. It's all over the place. Some elements are up, some elements are down. Very, very different. The chemistry is fundamentally different, and the thing that really leaps out at you is that there's several elements in particular that are highly enhanced in this rock. Phosphorus, sulfur, chlorine, bromine. These are all elements that tend to be present in salts. These are all elements that tend to be mobilized by liquid water. So this is a clue that liquid water was involved. This is some data from our Mossbauer spectrometers, which tells us what elements or what minerals are present. The black dots are the data. The blue and red and yellow and green correspond to the different minerals that are there. And one of the minerals there is a mineral called goethite. Goethite is an iron oxyhydroxide. It actually has water in its crystalline structure. You have to have water to make this stuff. So we now have conclusive evidence that these rocks were once soaked in liquid water. As we've worked our way up, we found other rock types. This is a strange one. This is a rock that we found really just in the last couple of months. This is an outcrop that we call alligator. This stuff is finely layered, and it is made of grains of sand that are glued together with magnesium sulfate salt. This is a sandstone, and it's glued together with sulfate salts. You can see, here are the grains. It's just encrusted with this stuff. Again, water has to have been involved here. This is one of the craziest things that we found of all. This was just in the last few weeks. This is a patch of soil that we named Paso Robles, and this was complete luck. Absolute, complete good luck. I remember this very well. We have these. This is one of these pictures that I told you about from those front googly-eyed cameras. We do send them down to the ground occasionally, and there was a day that we were driving. We were driving up a steep hill, and we were trying to drive backwards. Sometimes we drive forward, sometimes backwards to make it easier on the vehicle because it can go both ways, and it's less wear on the gearboxes that way. And we had tried to back up a hill and failed. We just slipped and churned and dug up sand with our wheels. And we looked at the sand, and we thought, geez, that looks awfully bright. So we took a color picture. This is what it looks like. This stuff is 60% salt. So it's the saltiest place ever found on Mars. You could taste it. Most of it's iron sulfates, some of it's some phosphates. Very strange stuff. Don't know how it got there. But again, it can't be any process other than, at some level, water coming up to the surface and evaporating away and leaving salts behind. This is Larry's lookout. Now, we've gotten to the part of the Squyres presentation where the data, this picture only just came down in the last week or so. So we haven't really processed it very well, so no, the sky's not blue. But this shows Larry's lookout. We've gotten to the crest. This is Cumberland Ridge. There's Tennessee Valley in the background. And as of today, Squyres is here. These are two views looking backwards. That's Larry's lookout there. This is a better close-up view. There's the lookout right there. And you can actually see, there's a structure to this. It's got kind of a planar structure, and it lines up with these other planar structures in the rocks all the way across the valley. So we're starting to do real geologic mapping here. And that's where Squyres is right now. In the future, we're right here. We're planning to go to the summit of Husband Hill and then across to the other side and down into the thing we call the inner basin. In the last few weeks, a miracle has occurred on Squyres. This is what Squyres looked like 330 days into the mission. It was filthy. Dust settles out on the solar arrays. The day that we landed, with the arrays as clean as they had been back in Florida, we were getting 900 watt-hours of energy. That's enough energy to run a 100-watt light bulb for 9 hours out of those solar arrays. By the time this picture was taken, that 900 had dropped to about 400 because they were so dirty. Then it got down to about 350. Death is at 280. And then this happened. We saw some dust devils, little mini tornadoes out on the plains. And over a period of just a couple of days, this is our calibration target for our camera, it went from looking like this to looking like this. We went from 350 watt-hours, 70 watt-hours above the death zone, up to yesterday, 829. Squyres looks like it just came off the showroom floor. Sometimes you get lucky. Watch carefully. That's an eclipse. First eclipse ever witnessed from the surface of another planet. Mars has 2 moons, Phobos and Deimos. And this is Phobos eclipsing the sun. There's no science in this at all. We just did it because we could. That's a meteor. This one got our attention. We were taking a picture of the sky at night, and there's this streak. There's something streaking across the Martian sky. So we got excited about this. Initially, we thought it might be a spacecraft. No, wait. There are spacecraft in orbit around Mars. There are live, healthy spacecraft, and there are all dead spacecraft still orbiting the planet. The Mariner 9 spacecraft, still up there. The Viking orbiters, they're still up there. We thought this might be the old Viking 2 orbiter, and then a research group in France did a very interesting calculation in which they calculated when and where meteor showers should be seen on Mars. And this came at just the right time and just the right orientation to be a Martian meteor. So that's what this is. We all waved. We took this one. You can just see Earth hanging in the sky above the rim of Gusev crater. So that's Spirit. Let me go on to Opportunity. Opportunity's landing site was chosen for very different reasons than Spirit's. Spirit's was chosen on the basis of the landforms, the topography. There's a hole in the ground. There's a dry riverbed flowing into it. There's topographic evidence that there was once water there. Here the evidence was in the chemistry. Meridiani is very smooth, very flat. Meridiani Planum is the name. It is an extremely smooth, flat place. What sets it apart is not anything particular about the topography. It's the chemistry. This is an image, shows Martian craters, and the streaks that you see across here are data from a spacecraft, Mars Global Surveyor, that has an infrared spectrometer that can detect minerals. The blue stuff is lava, it's basalt. The red stuff, which is where we landed, is where this infrared spectrometer detects a mineral called hematite. Coarse crystalline gray hematite. It's an iron oxide, and it's a mineral that sometimes, not always, but sometimes forms as a consequence of the action of liquid water. So this was like a chemical beacon visible from space telling us that water may once have been here. So it's an interesting place to go. The thing that made me nervous about Meridiani before we landed there was that I feared that with the topography being so smooth and so flat, it would be hard for us to find any topographic slopes that would expose any rock at all. I need not have worried. I'm not a golfer, but after seeing this, I'm starting to think that maybe I should take it up. This is a set of images. These are 3 images. This is looking down. This is just the same thing viewed obliquely. These were taken from our spacecraft as it fell towards the surface. That little black dot there, that's the shadow of the parachute. Okay? And the red shows the trajectory that the spacecraft followed as it descended. So we're coming screaming in from space. We're going 400, 300, 200 miles an hour. We fire our rocket motors right here, zero out the velocity, cut the airbags free. They begin to bounce and bounce. The wind, which is blowing from the south, curves the trajectory, starts heading towards the north, and then reading the green perfectly, it just bends to the left and goes right into that little impact crater. Tiger Woods on his best day could not have done this. And when we opened our eyes, we found exposed within the wall of this lovely little impact crater, smaller than the room that we're in, this wonderful outcrop of layered bedrock staring us in the face. Now, when we first saw this, when the very first pictures came down, this looked very imposing. Looked dangerous. We called it the Great Wall. Then we figured out how big it really was. Great big rover, little tiny outcrop. But the small size was part of its charm, because what that meant was that these layers that we were seeing were very fine. This is not something that lava does. We knew immediately that we were dealing with something sort of different. We went looking right away for the hematite. We found it right away. This is data from our infrared spectrometer. Red is lots of hematite. Blue is none at all. And you can see that out on the plains outside the crater, there's a lot of hematite. There's a little bit in the outcrop, but not a whole lot. There's some down in the crater. And then on the crater floor, there are these splotches, which show up in blue where there's no hematite. The splotches are airbag bounce marks. So somehow when you bounce on the dirt, the hematite goes away. That was our first of a number of puzzles. These are the airbag bounce marks themselves. I mean, look, you can see the seams. You can almost see the stitching. It's as if they were pressed into talcum powder. And yet, everywhere else, there's this gravel. And then somehow the gravel disappears when you bounce on it. So we'd spend a day or two fighting about what that meant. We began to look at the gravel closely. And we started to notice that some of the grains, many of the grains, looked awfully round. We drove off the lander. We whipped out our microscope. We looked at them carefully. I still remember, I will always remember to the day I die, where I was standing and how I felt when this picture hit the ground. This was the moment at which we realized that we were dealing with something truly unusual at Meridiani Planum. The surface is littered with an uncountable number of little round things. 4, 5, 6 millimeters in diameter. And all we knew at this point was they were little round things. This will drive you crazy if you stare at it for too long, but what this is, we have one of our spectrometers has a little contact plate on the front end of it that you can push down, and then you can take it away and take pictures. And this is just a picture of some soil before and after the contact plates hits, and now you can see what's going on. The grains, the gravel, which are sitting on top of the sand, get pushed down, and they just submerge, right? They disappear from sight. Airbags did the same thing. So this is our first hint that the hematite, which disappears when you press on something, is in the gravel. We drove over to the outcrop. It was only 8 meters away. Took a close look at it and realized that this stuff isn't just layered, it's laminated. I mean, the individual layers are just a millimeter or two thick. Very, very finely layered. And then what we discovered was that when you looked at it closely, these little round things are embedded within the rock, like blueberries in a muffin. Okay, you can see them. This is just a rock. Here's the same thing, and the infrared wavelengths really processed so that you can see the color contrast. And the orange things, those are the blueberries in the muffin. And they're in the rock. And they're harder than the rock. The rock erodes away, and then the blueberries fall out and roll down the slope. Pile up down here. Crazy. Here you can see, this is a close-up with the microscope. You see these very fine layers etched by the wind, and then there's a blueberry kind of waiting to jump out of the rock. As we looked at more and more of these blueberries, we began to notice some things about their character. They were, for the most part, very round, but there were some variations. Sometimes you'd see doubles, where there were two that were sort of merged. In a number of places, we would see kind of a stripe running across them, like the stripe on a croquet ball you can see here. And wherever we saw those, they would be parallel to the layers in the surrounding rock. All of these things are characteristic that are typical of things on Earth called concretions. Concretions form in water-saturated sedimentary rock on Earth when the water has dissolved in it some stuff, some mineral that wants to precipitate out, wants to solidify. What will happen is there will be some little nucleation point around which the solidification will begin. And then it will add layer upon layer upon layer, building up a spherical shape in the same way that an oyster builds a pearl, and growing these little hard mineral accumulations within the soil. Now, one mineral that does form concretions on Earth is hematite. And so we were very, very interested in confirming beyond a shadow of a doubt that these blueberries were really made of hematite. We had hints, but we didn't have proof. Now, one of our spectrometers is a very good hematite detector. And so what you'd like to do is you'd like to just go up to a blueberry with the hematite detecting spectrometer, put it right on it, and find out what the sucker's made of. Okay? Problem is the blueberries are little tiny things, and the field of view of the spectrometer is a lot bigger. So if you try to make that measurement, you get lots of background and just a little tiny point in the middle. What we needed was a gathering of blueberries. So we found one. This is a place where there was a little bowl-shaped depression in the rock, We called it the berry bowl. And a bunch of berries had just, happily kind of gathered there conveniently in this berry bowl spot. And we stuffed our spectrometer inside. The yellow stuff is kind of background, and the blue stuff is the berry bowl. And that distinctive six-peaked blue spectrum, 1, 2, 3, 4, and then there's 2 that are buried in here. That spectrum is the definitive spectral signature of hematite. So the blueberries are made of hematite. And at this point, we began to really believe that these things were probably concretions, and we still do. We grew curious about what the rock was made of. And here we made a remarkable discovery. This is a spectrum from our X-ray spectrometer. It tells you what elements are present. Each one of these little peaks corresponds to a given chemical element. So, for example, that's iron there. And the blue curve is the outcrop. And look at sulfur. Red is kind of average Martian soil. That's the outcrop. There is a huge amount of sulfur in this. There is so much sulfur in this that the rocks have to be 30, 35, 40% sulfate salts. So these are rocks that are made largely of salt. One of the salts that's present is one called jarosite. I've shown you a spectrum like this before. This is from the Mossbauer spectrometer. The yellow stuff, that's the jarosite. Jarosite, here's the chemical formula up here. It's got OH. It's got water locked up in its crystalline structure. You have to have water to make jarosite. So again, this is evidence that there was water here. And interestingly enough, just about every place on Earth where jarosite is formed, it's precipitated not from neutral water, but from acid. So this groundwater, this water at Mars, may have been sulfuric acid. As we were looking at the rocks with our spectrometers, we were also looking at them with our cameras, and we began to notice that there were places where the layers looked funny, where the layers didn't quite seem parallel. We decided we wanted to investigate this in more detail, and so what we did is we went over and we looked at it carefully with our microscope. This is a rock that is about the size of a football. We took 120 pictures of this thing with our microscope, mosaicing them together. What we were looking for was this. If you've been to a beach, if you've looked in a stream bed, you've seen this. This is what happens when water flows over sand. This is from experiments that were done by Dave Rubin at the U.S. Geological Survey right across the bay here in Menlo Park. And what he did was flow water over sand. That's only 40 centimeters, like a little more than a foot across. And you can see you get ripples. The ripples propagate downstream, and look at the ripples' crests. They're not straight. They're very sinuous, up and down, up and down, up and down. That's the signature of water moving over sand. Here it is, simulated in a computer. There go the ripples, sinuous crests, water moving over sand. Wind doesn't do this. And here's the key. Remember, geologists are like detectives. Okay, here's the clue. Look what's left behind. You don't get parallel layers. Instead, you get these little smiley shapes. See that? Little smiles. That's what's left behind in the geologic record when you have these propagating ripples. Here's the real thing from some sediments in the Colorado River. Little tiny smiles. Then you look at the rocks on Mars with a microscope, and you follow the layers, and look what you see. Little smiles. We smiled when we saw them. Okay? Here's another one. I mean, try to find parallel layers anywhere in that rock. Okay? But up here, all in here, you see the little smiles. So this is evidence not just that water soaked these rocks, but there was water at the surface. There was liquid water. Now, I don't know how deep. Up to my ankles, up to my knees, up to my neck, over my head, I don't know. But water flowed across the surface at this place on Mars once upon a time. So, after spending 60 glorious days in our little impact crater, made kind of a mess of the place actually, we left. We headed out across the countryside. The first place that we went was another crater that we named Endurance. Everything that we had hoped Bonneville would be, Endurance turned out to be. Endurance turned out to be this wonderful 10-meter deep window into the subsurface of Mars, exposing many meters of layered rock within the crater. This is what we'd hoped for at Bonneville. We got it here. We spent 8 months studying this crater. It's a dangerous place. That cliff there that looks overhanging, it is overhanging. This is the kind of place where if you're a little rover and you're not careful, you can fall off a cliff and die. So we were real cautious. Spectacular topography. And you remember that image that I showed you earlier with the little tiny outcrop and the great big rover? That's the scale here. So we were very careful, but I will tell you that after 6 months of very cautious and then later very aggressive driving, we managed to get that little rover to right there. We took a picture from right there. I'll show it to you. We didn't drive down the cliff. We went around. Now, we were very interested in going into the crater because that was where the geology was. The beautiful thing about layered rocks is they preserve a record of time, with the younger rocks at the top and the older rocks at the bottom, and if you can drive down, it's like traveling back in time on Mars. We were very confident that the rover could drive into the crater, but we weren't sure if the rover could drive out. We did not want it to become a permanent rover trap, and so we built this test fixture at JPL. Here it is here. It's full of sand and rocks. I had graduate students out there gluing little BBs onto the rock to make blueberries. The thing that I love about this picture, we actually built four rovers. 2 of them were Spirit and Opportunity. 2 of them are on Earth. This is one of the Earthbound rovers. The rover's in the sandbox, is doing the test. It's all on its own, but the technician who's conducting the test has to wear a safety harness and a rope because it's so steep. It turns out that the rovers were very good climbers. They can climb slopes up to about 33 or 34 degrees. And so we went in. This is just Opportunity looking at her shadow as she first went over the lip and down into the crater. As we worked our way down through the crater, we came upon layer upon layer upon layer of these sedimentary rocks, working back in time deeper down into the crater. Every time we got to a new layer, we'd put in a rat hole and we would study the chemistry, the mineralogy, the texture. This is about 6 or 8 weeks of work right here. You can see the wheel tracks there and there, enhanced color here. But there's 1, 2, 3, 4, 5, 6, oops, I missed one, 7. 7 rat holes for every one of those. Every time we got to a new layer, new hole, new chemistry, new mineralogy, new microscopic images, everything, putting together the first stratigraphic section, as a geologist would put it, ever done on another planet. We did 7 of them up there, and then 8, 9, 10, a total of 11 over a total vertical distance of almost 10 meters, working our way down into the crater. This took all summer, like May through July or August of last year. Things changed as we went down into the crater. Near the top, very fine layers. You can see the little ripples, blueberries. Once you got deep down, it all changed. The layers aren't there anymore. All the salts have completely recrystallized. They've wiped out the layering. This stuff has been pickled. It's been soaked in liquid water for so long that the salts have recrystallized to give you the texture that you see there. The chemistry changes. This is just a plot. This is at the top. This is working our way down. So this is the highest. This is the lowest. This shows how much magnesium and sulfur, how much chlorine there are. Magnesium and sulfur go down, down, down. That's magnesium sulfate salt being dissolved away. Chlorine goes way up. That's chloride salts being deposited. Again, this stuff was pickled. It was soaked in liquid water beneath the surface. There's a dune field at the bottom of the crater. We nearly got stuck in it. Kind of a scary moment. Pretty pictures, but we nearly got stuck in these dunes. We got out. We saw some very strangely shaped rocks down in the crater. This is the one that we initially called the petrified Martian dinosaur brain. It's a big one. This thing was like 1 meter across. Don't know how it got that way. This is a good one. Guy on my staff, when he saw this, said, now that's what a rock from another planet should look like. I don't have an explanation for that, but it's cool. We drove up to the base of that cliff. We drove down into the crater to the dune field, then up to the base of this cliff. This is a picture taken from that spot that I showed you. This display does not begin to capture the richness of what is in this image. So I'm going to take just this little tiny bit of it right here, and that's what it looks like. The whole picture is that good. And it preserves this incredible record of the initial deposition of the sediments and then the way they were changed as they were soaked in liquid water. We're going to be studying this stuff for a long time. After 8 months in Endurance Crater, we decided to go someplace different. So we climbed out of the crater, as we always claimed we would. And the next place that we went was our heat shield. You recall from the video that the heat shield drops off the vehicle as it's plunging towards the Martian surface. And the heat shield, we're done with the heat shield. We don't need it anymore. We just let it fall away. And it hits the ground going about 200 miles an hour. This is what it looked like in Florida. And then this is the junk pile formerly known as the heat shield. After it hit the ground, it sort of belly flopped, made this round divot, and then landed here. Now, the reason we went here was not to study Mars, it was to study heat shields. People have been designing heat shields to work in the Martian atmosphere for more than 30 years, but no engineer who has designed one of these things has ever gotten a chance to see their handiwork after it worked. Did it almost burn through? Did they build it much thicker than they needed to? How did it perform? What we really wanted to understand was, how did this thing do? So we went up to it, took pictures of it close up with our cameras. It was kind of a wreck. Looked at it carefully with our microscope, provided a lot of good data for the engineers. As we were doing this, as we're sort of concentrating on the heat shield, the PanCam camera, the one at the top of the mast, is looking around for other things. And we saw this right next to the heat shield. We called it heat shield rock. Sometimes the imagination just doesn't kick in when you need it. We went over, we investigated this thing. It is not a rock. It's a meteorite. This is a nickel-iron meteorite sitting on the surface of Mars, 2 meters away from the heat shield. I told the team we shouldn't stay here long. This is obviously the place where big metal objects fall from the sky. But this thing is a meteorite. It's the first meteorite found on another planet. Since leaving the heat shield, we have been blasting our way south at breakneck speeds. Maximum is 220 meters in a single day. Heading to the south across nearly featureless plains. We are now about 1 week away from reaching our target. Let me show you the scale here. Now, this is turned so that south is that way, north is that way. That's a 500-meter scale bar. We landed in this crater here. That's Eagle Crater. We drove to this crater here, 800 meters. That's Endurance Crater. We spent 8 months there. Since leaving Endurance Crater, let's see, we were at the heat shield at Christmas. So we left Endurance Crater. We went to the heat shield with this little dark splotch here. We have then driven here, all the way across here, past here, to this crater, and now to this crater. Right now, this is these 2 craters we named Viking and Voyager. Right now, as we speak, Opportunity is parked with its wheels right on the lip of Voyager crater. These 2 craters are the gateposts to this stuff. We've been driving across these gray, featureless plains where the only interesting things are craters. But now, we're about to get into this. This stuff is called etched terrain. It's a geologically meaningless term. It looks etched when you look at it, but how it formed, what it is, we do not know. We suspect that it is layers of the same kind of sediment, but exposed not by violent impact processes, but rather by gentle erosion by the wind over hundreds of millions of years. And so we hope we will be able to go in there and read that geologic record, but instead of reading a record that has been jumbled and busted up and mangled by the cratering process, see a record that is much more pristine. I do not know if this is going to be smooth sailing or if this is going to be an impenetrable badlands that we cannot drive through. But we are only a week or 2 away from getting into it, and soon we will know. So we'll see. We're likely to spend a lot of time into the etched terrain. There's an awful lot of it if we can get through it And if the rover survives, then out here is Victoria Crater. 900 meters in diameter, 40-meter cliffs of layered sedimentary rocks. This is a place that I would love to get to if we can possibly make it. We'll see. Whenever I talk about this mission, I always end with this slide. This mission was brought about by an incredibly dedicated, very large, and very talented team of scientists and engineers. I'm just one member of the team. Here are a bunch more. This is down at the Cape in Florida with Opportunity in the background right before we sent her out to the pad. For all of us who have had the enormous privilege of participating in the mission, it has been, in the very literal sense of the phrase, the adventure of a lifetime. And I want to thank you for inviting me here tonight to tell you about it. Thanks. That's a good question. The question is basically, how much water is there still on Mars? Very tough question to answer, because right now we suspect that what ice there is and what water there is either locked up in the poles as ice, where we know there is some and we can sort of measure the quantity there, or we suspect that a substantial fraction of it is locked up beneath the ground as permafrost, or maybe if you go deeply enough, you get to levels where the temperatures are warm enough that there's actually liquid beneath the surface. People have tried to make estimates of the volume of water that might be there, and you get numbers that are, a layer of water equivalent to a few tens of meters or 100 meters or so, sort of uniformly covering the planet. But those are wild guesses. And the answer is, until we have tools that can see deeper, we're not going to know how much, and we're not going to know if there's any liquid. To date, nobody has ever found any liquid water on Mars. It's actually pretty hard to lose it to space. You have to photo-dissociate it, and even then some of the molecules or some of the atoms are hard to get rid of. Way in the back. Yeah. The question is, are you as tired as you look? Is that what you were saying? The question had to do with the unexpected lifetime of the vehicle and the exhaustion level on the operations team. We're very, very tired. I mean, I'll be really honest with you. We are very tired. Now, we signed up for a 90-day mission. That doesn't mean that we expected the wheels to fall off when the sun came up on day 91. It does mean, however, that was when we began to be operating outside the realm of what we had tested for. If before we landed, if you had given me truth serum and said, okay, Squyres, how long do you think these things are really going to last? I would have said, if we can get through the unfolding part and get down on the surface, we could get 120, 150, if everything went right, maybe 180 days out of these vehicles. Today is day 448. And we've got as much solar power as we had the day we landed, practically. So I do not know how long these things are going to last. For the first 4 months of the mission, the operations team, all of us, lived on Mars time. The Martian day is not 24 hours and 39 minutes long, or not 24 hours long, it's 29 hours and 39 minutes long. And that 39, you might think it would be nice to get an extra 39 minutes of sleep a night, but that 39 minutes really messes up your life, because what has to happen is your cycle shifts. You lock up with the planet that you're working on, not the one that you're living on. And so, for example, if my daily operations planning meeting is at noon today, then when you're on Mars time, tomorrow's at 12:39. The day after that, it's at 1:18, and it goes around, and 2.5 weeks later, you're meeting in the middle of the night. And we all just cycled around, and we had blackout shades on the windows, and we had blackout shades in our apartments. We got a bunch of radio alarm clocks and hacked the electronics so they would run on Mars time, so we could try to find one of those at Walmart. And I've got a Mars time watch that I still keep with me. And it was tough. It was tough. The worst part was changing rovers, because I got a big team, 170 scientists. We're all living on Mars time, but we got 2 different rovers in 2 different sides of the planet, so I got to split my team in half, and so now they're living in 2 different Martian time zones. And if you're working on Spirit and you want to switch to Opportunity, you get Martian jet lag. So it was pretty bad. After 4 months of that, we decided, okay, we've had enough of that. So we went to sort of a quasi-Mars time, quasi-Earth time, which we're still living with now, where we kind of stay with Mars time for a while, and then we kind of snap back and wait for it to come around and catch up with us. It's confusing. But we're tired. We're very, very tired. After 8 months, where we were all living in Pasadena and working at the Jet Propulsion Laboratory, we decided we'd had enough of that, too. And so we all packed up, and I guess last summer, last July and August, we spent a lot of time and effort investing in video conferencing and teleconferencing and everything that we needed for remote operations. And so now I can, we can do flight operations from home. So I can drive rovers on Mars all day and then go and sleep in my own bed at night, which is nice. But we're tired. Now, I wish we could. In order to do, you can make guesses. I mean, you can point at those rocks and you could say, boy, rocks that look like that on Earth tend to form this fast, but it's Mars, and I don't feel comfortable doing that, okay? There is no piece of hard data that we can point to that dates anything, other than relative ages. These rocks are younger, these are older. But no, the only way to do it, and this is really an important point, is to get rocks from a place like Meridiani Planum back to Earth, and to put them in the best laboratories on Earth where we can do radiometric age dating and we can really find out what they're made of, take those blueberries, take the sulfates apart molecule by molecule, find out what's in them. We have shown that there was once a habitable environment on Mars. The next step is to find out if it was inhabited. And to do that, I think we ought to bring rocks back.